look at some gas laws, which are mathematical equations that describe how gases behave. We're going to look at how change the pressure of body will affect gases. So before we can do that, let's make a few definitions. Pressure, when you think about pressure, the definition is force pushing on a unit area of surface. So it's sort of like pushing gas, like putting my hand on something, putting some force and trying to just have it on a certain area of the desk and pushing on it over a certain unit of area. So I can put my hand on the finger and try to push the desk, and of course that would not be as much pressure as if I was wobbling through it over a bigger area. So pressure just has to do with how much force is over a unit area. So look at the next example. If you have an inflated balloon, it will be actually the molecule pushing on the surface. If you let the balloon inflated, the molecules inside are actually hitting the walls of the balloon, keeping it inflated. So the force is the pressure. First also, let's talk about atmospheric pressure. You probably heard that in the weather reports or whatever. The atmospheric pressure, this has to do with the molecules of air that are constantly moving around us. So as the molecules hit us or are pulled down by gravity and hit different things, that's what causes atmospheric pressure. The higher you go in altitude, the lower the atmospheric pressure because there are fewer molecules in the air. So one way to measure pressure is to use a barometer. And this picture on the slide is a barometer, sort of old-fashioned barometer, where you take a tube of filled with mercury, you invert it into a shallow bowl of mercury, and then some of it will run out, so that causes a vacuum at the very top. But now all of the mercury doesn't run out into the bowl, and what's keeping it from running out is the atmospheric pressure. So the pressure of the molecules on the surface of the bowl are keeping the mercury up in that column. Now, of course, the column might go up or down, the column of mercury, depending on the atmospheric pressure. If the atmospheric pressure rises and there's more pressure pushed on the bowl, then the mercury inside the tube will rise up. If the atmospheric pressure lowers, then more of the mercury will run out of the tube, and then the height will be lower. So one way to measure pressure is in millimeters of mercury. So you actually measure how high that tube of mercury is, and so that's where millimeters of mercury comes from. Standard pressure is 760 millimeters of mercury. Sometimes the unit torr is also used. So 1 torr is the same as 1 millimeter mercury, so 760 millimeters of mercury is the same as 760 torr. Torr is a name given by a scientist, Torricelli, who did some of the gas investigations hundreds of years ago. The pressure unit that we are going to use most often is called atmospheres. 1 atmosphere is standard pressure, and it's equal to 760 torr. So that's something to keep in mind. If you want to convert from torr to atmospheres, you have to divide by 760. All right, temperature. We've talked about this in previous units, but the temperature is just a measurement of the average kinetic energy. The temperature unit that we use in everyday life, we use Fahrenheit, and of course in most science we use Celsius, but for the gas laws we're going to have to use the absolute or Kelvin temperature scale. To find the temperature in Kelvin, all you have to do is add 273 to the Celsius degree. We use the absolute scale because 0 in an absolute scale means 0. If we were to talk about 0 degrees Fahrenheit, that's where it's actually below freezing. Freezing in Fahrenheit would be 32 degrees. But it doesn't mean that there's no heat at all or no molecular motion at all. So on the absolute scale, a 0 Kelvin means absolutely no heat, and molecular motion has totally stopped. And so that's why we use the absolute scale. Also, because we'll end up dividing by temperature sometimes, and you can't divide by a 0, so you can't have anything below 0. Okay, and then volume, of course, you know what volume is. It's just the size of the container in which the gas is placed. The most common units that we're going to be using are liters or milliliters. And remember, if you need to convert from milliliters to liters, you have to divide by 1,000. Okay, so the first gas law is called Boyle's law. And Boyle's law says that pressure and volume are inversely related. So what does that mean? It means if one goes up, the other goes down. Oh, and temperature has to be kept constant during this time, so we're not going to change the temperature. So the average molecular speed will stay the same. All right, so a mathematical way that you can represent an inverse relationship is, as you see here, P1 V1 equals P2 V2, where the 1s indicate the initial conditions and 2 represents the final conditions. So if you have a particular pressure and a particular volume, and then you change the pressure, the volume will also change in response, and so that's where the 1s and 2s come from. The 2 will be after the change, the 1 will be before the change. An example of Boyle's law, as you can see here, is breathing. When you breathe in, the diaphragm goes down, your lungs will expand, so the volume increases. What happens then is the pressure decreases because the volume is increasing, the pressure decreases. Now the pressure inside your lungs is lower than atmospheric pressure outside your lungs, and so air naturally flows in. When you breathe out, your diaphragm pushes up, it compresses the lungs to a smaller volume, the pressure in the lungs increases, and now the air will flow out. If you're interested in looking at that website, it's a kind of a cute little, you can see, you can change pressure and volume and see what happens. But this picture on the right kind of gives you an idea. So on the left, we have a large volume, and then what we do is we push the plunger down, that's increasing the pressure, and so in order to, so as you increase the pressure, your volume decreases. Or you could also think of it the other way. If you want to increase the pressure, the way you have to do that is to decrease the volume. If you pull and make the volume bigger, then the pressure goes down. And remember, when we're talking pressure, we're talking how many times do the molecules hit the walls. And so in the larger container, the walls will hit less often, which means the pressure is lower. And as you decrease the volume, there's more chance for the molecules to hit the sides of the wall, and so pressure increases. Charles's law is the relationship between temperature and volume. Temperature and volume are directly related. So what does that mean? If you increase temperature, volume will increase. If you decrease temperature, volume will decrease, or vice versa. If you increase volume, temperature will decrease. If you increase volume, temperature will increase. If you decrease volume, temperature will decrease. So they're constant. They go in the same direction. You can see over here an example of Charles's law is the air inside a hot air balloon. If you heat it up, what happens is the volume will expand. The pressure is going to stay the same because the pressure is trying to sort of compete with the atmospheric pressure around it. But so in order to keep the pressure the same, the volume is going to have to expand when the temperature increases. Another thing is if you take a sealed balloon and you put it in the freezer, it'll get smaller. The volume will go down as it gets cooler. So why is that happening? You can see in the picture to the right. Now remember that pressure in this case is kept constant. So remember, pressure is how many times the molecules hit the wall. So if you have a particular or low temperature at a particular volume, you can see V1 and T1 on the left, and then if you increase the temperature, remember that you want to keep the number of molecules hitting the walls the same, so the only way you can do that is to also increase the volume. So as the temperature increases, volume increases. As temperature decreases, volume decreases. Gay-Lussac's law then is the relationship between pressure and temperature. And pressure and temperature are also directly related. Now, volume is kept constant.
So mathematically, a direct relationship is P1 over T1 equals P2 over T2, or divided by T2. Again, ones indicate the first set of conditions, and twos indicate the final or second set of conditions. So if you look at the pictures on the right, you can see that at low temperatures, the molecules are moving slowly. If you keep the volume the same size, then it's kind of low pressure. If you increase the temperature, you can see there the temperature's increased by 3. What happens is the molecules move faster, and in order for the molecules to stay, to have the volume stay the same, we're going to have to put more pressure on top to keep it, because if the volume could move, then the molecules would push it up. But in order to keep the volume constant, we have to keep an extra weight on top, which means extra pressure. So an example of Gay-Lussac's law is that you should check your car tire pressure before you start driving, because as they heat up, pressure will increase. So if you want to get a very accurate check on your tire pressure, do it before it gets warm. Also, if you've ever opened an oven, you may feel that quick flow of hot air. That's because as the molecules inside the oven heat up, the pressure builds, and then when you open the door, the pressure kind of comes out at you. All right, we can combine these three gas laws in what we call the combined gas law, and it's sort of the easiest one to remember, and you see there P1 V1 over T1 equals P2 V2 over T2. So again, one set of conditions and then changing to a new set of conditions, and if one thing changes, the others have to change in response to keep that equality going. You can remember this combined gas law, and then instead of the last three, because this is made up of the last three, and so if you remember this and then you think, oh, well, temperature stays constant, which is Boyle's law, then you can just cross the temperature out, and then you have P1 V1 equals P2 V2. If pressure stays constant, you can cross those out, and you have Charles's law, V1 over T1 equals V2 over T2. If volume is constant, then you can cross volumes out, and so then we have Gay-Lussac's law. So if you remember the combined gas law, you can get the other three when one particular property is held constant. And again, you might want to check out some of those websites. They're kind of fun to play around with. So here's an example of the combined gas law, and this is, again, if you want to go either to that YouTube video to watch what's happening, or you can also go to that Steve Spangler Science website, and I think that shows you also a can crushing. If you take an empty can and you heat a little bit amount of water in the can, what happens is as you heat it, the volume of the water vapor increases, so it will start to expand and fill up the can, and what it'll do is it'll push all the air out. So now there's this water vapor is the only thing in the can. Then if you take it and flip it into cold water or ice water, what happens is very quickly the vapor cools down, so it condenses into a liquid. The gas condenses into a liquid. Now there's like a vacuum inside there because there's no more molecules. They've all condensed into the liquid. And so what happens is the outside pressure pushes on the can and it collapses, and it sort of implodes on itself. So you've got both Boyle's law and Charles's law going on in a soda can. And then another example, guns or cannons, what happens is if you have a bullet, there's a little tiny space of gas trapped behind the bullet, and then when you hit the powder and you light the powder, what happens is it gets very hot, and so the gas then expands dramatically. The pressure increases, and then eventually it gets to where it can't be held back anymore, and so it pushes. Because the pressure's high, volume has to increase, and so it pushes the bullet out of the gun. So again, these are all examples of gas laws. We can use the gas laws to solve some problems. So here's an example. Let's say we have a gas that is at 5 liters and 2.5 atmospheres of pressure. And if we change the pressure to 10 atmospheres, what's going to happen to the volume? Let's calculate the volume and constant temperature. So first of all, there's our combined gas law, P1 V1 over T1 equals P2 V2 over T2. if it's constant temperature, that means T1 and T2 are the same, so we can cross them off. So now we have Boyle's law. P1, V1 equals P2, V2. So all you need to do is plug the numbers in where they belong. So our first condition is a volume of 5 liters and an atmosphere pressure of 2.5 atmospheres. And then we change in the new pressure to 10, and what we want to do is find out what is the volume. So if you're not very good with algebraic equations, what I recommend, just go ahead and do all your math before you do anything else. So I took the 2.5 times 5 to get 12.5. So 12.5 equals 10V2. Then remember that you want to get V2 all by itself. So to do that, you want to divide both sides by 10. So on the right-hand side, both 10s cancel, and on the left-hand side, 12.5 divided by 10 gives us 1.25 liters. So let's take a minute and think about that. We started at 5 liters and 2.5 atmospheres. Then we increased the pressure to 10. So we know that if we increase the pressure, since these are inversely related, then our volume should decrease. And in fact, that's what we found. It went from 5 liters down to 1.25 liters. So sometimes just take a minute and think through your problem and see if it makes sense with what you kind of know already. Here's another example. This time all 3 conditions are changing. So what I recommend is go ahead and make a little bit of a chart. So here you can see I've made a chart where I have initial conditions and final conditions, P, V, and T. So let's read the problem. As the gas sample has a volume of 2.5 liters, it's at a temperature of 30 degrees and a pressure of 1.8 atmospheres. So that's our initial conditions. So I put in pressure 1.8, volume 2.5, and then remember that our temperature always has to be in Kelvin, so 30 degrees Celsius plus 273 gives us a temperature of 303 Kelvin. Now the problem goes on. What volume in liters will the sample have if the pressure is increased to 3 atmospheres and the temperature is increased to 100 degrees? So again, our pressure is increasing, so our final pressure is 3 atmospheres. Our volume is what we're looking for, we don't know. And then our temperature is increasing to 100 degrees Celsius or 373 Kelvin. So now that we have all our values, we can plug it into our equation. So you can see we've got our first set of conditions, 1.8 times 2.5 divided by 303. And then our second set of conditions, 3.0 times V2 divided by 373. So we keep V2 because that's what we don't know. If you have fractions, one of the easiest things to do to clear the fractions is to cross multiply. So I recommend doing that. There's other ways you can solve this problem, but if you're not super good with algebra, you might want to just cross multiply to clear the fraction. So you can see I've cross multiplied. That little 2 on the V should be subscripted. So now we have 1,678.5 equals 909 V2. Since we want V2 all by itself, we have to divide both sides by 909. So we get V2 equals 1.85. As I've done here, drop the units when you're doing the math, but then in the very end, make sure and put your correct units. So since volume was started in liters, the new volume will also be in liters, so 1.85 liters. Sometimes with these combined gas laws, you can't predict the answer very well because you're changing everything. So like if pressure increases, volume should decrease, but if temperature is increasing, volume increases, so it's hard to know exactly how it's going to turn out. But that's how you do a gas law problem, a combined gas law problem. All right, so here's one more problem. A container of gas has 25 liters and is at 75 degrees. If we condense the container down to 10 liters, so we're decreasing the volume to 10 liters, and we're keeping constant pressure, what will the new temperature be in Celsius? So in this case, since pressure is constant, we just cross the P's off, and so we're just working with V1 over T1 equals V2 over T2. V1 equals 25 liters, V2 equals 10 liters. T1, remember when we do these problems, it always has to be in Kelvin. Even though the question is asking for Celsius in the end, we're going to have to convert to Kelvin and then convert back. So The temperature 1 in Kelvin is 348, and what we're looking for is T2. So I left that as T on the bottom. I'm going to put T2. Again, when you've got fractions, cross multiply. So 348 times 10 equals 25T. Now it's really easy to solve 3,480. Then we have to divide both sides by 25, so we get T equals 139K. Now again, since the question is asking for Celsius, to get back to Celsius, we subtract 273. So 139 minus 273 gives me a temperature of negative 134 degrees Celsius. So I know I've talked kind of fast, but hopefully you can go back and look at these problems and see what I've done. So we can take those combined gas laws, and actually if we can do some other rearrangements that we're not going to worry about here, but the ideal gas law, actually you can use it when the amount of gas does not vary. Meaning we don't have two sets of conditions. So that combined gas law, we had two pressures or two volumes or two temperatures. In this case, we're going to see how temperature, volume, and pressure play out with respect to how many molecules there are. So the ideal gas law is PV equals nRT. So let's go through with what each variable stands for. So P is the pressure, and this is very important. When we're using this equation, pressure always has to be in units of atmospheres. V stands for volume, as before, and again in this equation we have to use the units in liters. T, of course, is temperature, and temperature always has to be in Kelvin. The little n stands for moles of gas. How many moles of gas do we have? And then if you plug all these things in, you can get R, which is a constant. Constant just means a number that never changes. So it's called the universal gas law constant, and it's equal to the number 0.0821. R is a specific number. It's always 0.0821, but it depends on the units. And so sometimes, so actually the units are 0.0821 liters times atmospheres divided by moles divided by Kelvin. So that's why the units have to be in the ones specified on this slide. So if you're given different units, you have to convert them first. So here's an example of a problem where you could use PV equals nRT. All right, we have a 2.5 mole sample of gas. It's in a 6.17 liter tank, so that's the volume, and it's at a temperature of 28 degrees. What is the pressure in atmospheres? So let's think about what we know. We don't know the pressure, that's what we're looking for, but we do know the volume, 6.17. We do know the number of moles, 2.5. We always know what R is. R is 0.0821. And we know that the temperature is 28 Celsius or 301 Kelvin. So we plug 301 Kelvin. Now if you do the multiplication on both sides, you have 6.17P equals 61.78. Then divide both sides by 6.17 because you want to get P all alone, and you find out that P is 10 atmospheres. So if you have 2.5 moles of a gas in 6.17 liters at 28 degrees, it has to be at a pressure of 10 atmospheres. That's what the gas laws are telling us. Okay, so I think these problems aren't as hard as maybe they look at first. So just again, if you keep everything lined up and you plug the correct numbers in and then just do all the math before you do any algebra, you can get the answer fairly easily. Just remember that you always want to divide the side with the unit, the unknown, to get it all alone. So in this case, 61.78 is divided by 6.17, so the P goes all alone. And don't forget to keep your unknown in there, the variable for your unknown in there. Don't lose it, otherwise you'll have nothing to solve for. Here's another example. How many moles of gas at 100 degrees Celsius does it take to fill a 1 liter flask to a pressure of 1,140 millimeters of mercury? Okay, so if we stop and think about it, again, I've listed over on the left, what's my pressure? 1,140 millimeters of mercury. But remember that pressure always has to be in terms of atmosphere. So the first thing I'm going to do, you can see over on the right-hand side, is I take my millimeters of mercury, I have to divide by 760 to convert it to atmospheres. So 1,140 millimeters of mercury is the same as 1.5 atmospheres. So that will be my P. Volume is in liters already, so I can just leave it at one liter. My temperature has to be converted to Kelvin, 373 Kelvin. And the R, of course, is always 0.0821. So if I plug those numbers in, do the multiplication, I have 1.5 equals 30.62 N. Divide both sides by 30.62, and I get 0.049 moles. Don't forget to put your units at the end. You don't have to have them when you're doing the math, but go ahead and go back and put the units in at the end so that you know what we're talking about. Okay, so that's how many moles would be at 100 degrees in 1 liter at a pressure of 1.5 atmospheres. All right, so here's one more example. This one is a little bit tricky. What volume would be occupied by 100 grams of oxygen, O2 gas, at a pressure of 15 atmospheres and a temperature of 25 degrees? Now be careful here because the O2 is given in grams and not moles. Remember that little n is moles. But since we know back from Unit 2 how to convert grams to moles, we can do that very easily. So look over on the right-hand side and you can see 100 grams of oxygen divided by 32 grams per mole, because each oxygen is 16, so 16 times 2 is 32. Then we get 3.125 moles of oxygen. So N equals 3.125. The others you can see, P is 15 atmosphere, R is 0.0821, which it always is, temperature is 298 Kelvin. That should be an equals 298 Kelvin. So if we solve this problem, as you can see, we multiply everything, divide by 15, and we get 5.1 liters. So at this point, you might want to go and try, there's a worksheet, a gas laws worksheet that can help you work through some of these problems, and then the answer key to check yourself. But I'm just going to go ahead and finish out this slideshow. Just a couple of other little issues about gases and pressures. So Dalton's law of partial pressure says that if you take a mixture of gases, and if you know the pressure of each individual gas, then if you mix them together, the pressure should be the total of the two pressures if they're by themselves. So the picture sort of describes this. So if I have the little orange circles, the pressure from the little orange circles in one container and the pressure from the brown triangles in the other, then I put all of those together in one container, then the total pressure should be the original pressure of the circles plus the pressure of the triangle. So you can think of, say, if I have you've got air, which is a mixture of nitrogen and oxygen and carbon dioxide and some other minor gases. If I was able to just take all of the nitrogen and put it in one container and measure its pressure, and then take all the oxygen and put it in another container and measure its pressure, and then all the carbon dioxide, they would all be less than 1 atmosphere, but if I added them all together, they would give me the pressure in the room, or if it's standard, 1 atmosphere. So Dalton's law of partial pressure is not really hard. You just know that if you have lots of gases, you can add each pressure together to get the total pressure. Now another topic is vapor pressure. So what is vapor pressure? Well, we know that if a liquid boils, what's happening is the molecules are pulling away from each other. Well, that happens to a little extent when you just have a liquid sitting at regular room temperature. What happens is when we talk about molecules moving fast or slow, it's not that every single molecule moves at the same speed. They all have sort of a different They have an average speed, but some move slower and some move faster. So let's say I have a container of liquid sitting at room temperature. Some of the liquid molecules are moving fast, some of them are moving slow. Well, there might be some moving fast enough that even though we don't heat them up, they might be able to break away and turn into a gas. So you see on the right-hand side, you can see phase transition. So even though it's not 100 degrees, there might be a few molecules that have just enough energy to escape the liquid. At the same time, some of the gas molecules are going to be moving slowly, slower and slower, and eventually they might get captured by the liquid and pulled down into the liquid. So you've got, with any liquid, you have a few molecules of gas above a liquid. That's called the vapor pressure. So it's not really it's not at the boiling point, but just at any temperature. The vapor pressure is a physical property, and it will be different for every compound depending on the molecular interaction. So if you have something with really strong interactions, the vapor pressure will be lower because fewer molecules will be able to escape. If you think about what happens when you open your gas tank, sometimes if you're very low on gas, you've got a lot of gas molecules, gasoline. The gasoline is a liquid. Gasoline has a very low vapor pressure. A very high vapor pressure because it has very weak interactions. And so the molecules can escape very easily. So if you have a tank, your gas tank that's empty, and you've just got a little bit of liquid, and you hear that whoosh, when you open it, well, that's because it's high vapor pressure in there. On the other extent, water actually has a fairly low vapor pressure because it has very strong interaction. So the vapor pressure depends on the liquid. So actually, let's think about that same container at room temperature, and then let's start heating up that container. So we have at room temperature, there's a few molecules of gas, the vapor pressure. As we start to heat it up, what happens? More of the molecules have enough energy to escape. So our vapor pressure will increase as temperature increases. Now we're still not boiling yet. We could heat it, say, to 70 degrees Celsius. So there's a lot more, and if you've ever boiled a pot of water, you've seen that happen. You can see the vapor start to build up around the liquid. So it's still not boiling, but you have a higher vapor pressure because you have more molecules escaping into the atmosphere. Well, at the point where the vapor pressure equals the same as the atmospheric pressure around you, then the water starts to boil, or the liquid starts to boil. The temperature at which this happens is called the boiling point, or the temperature, the boiling temperature. Okay, so again, as you build up the temperature, more and more of the vapor, more and more of the molecules will escape into the vapor. Now, if they're still below the atmospheric pressure, it won't boil. But as soon as that vapor builds to atmospheric pressure, the molecules will start to escape rapidly and you have boiling. Now, the boiling point can happen at the temperature at whatever the prevailing atmospheric pressure is, which we'll talk about in a minute. When we say, oh, the boiling point of water is 100 degrees Celsius, what we mean is the normal or standard boiling point, and that is something that's measured when the atmospheric pressure is standard, or 1 atmospheres, or 760 torrs. So the normal boiling point is the boiling point at normal or standard pressure, 1 atmosphere. So we talked earlier about elevation. So atmospheric pressure actually decreases as you go higher in elevation because there are fewer molecules, fewer air molecules. So what that means is that the boiling point will actually be lower at higher elevation. So in the mountains, the boiling point is a little bit lower than it is at sea level, because at sea level you have higher atmospheric pressure. Up in the mountains you have lower atmospheric pressure. So this chart shows you that, for example, at sea level, the boiling point of water is 100 degrees Celsius. Abingdon, which is at about 2,100 feet above sea level, the temperature, the boiling point is 98 degrees Celsius. If you were to go measure your water boiling, you'd probably get it to be right around there, 98 degrees degrees. Salt Lake City at 4,000, over 4,000 feet, has a boiling point of 91. Because the atmospheric pressure is lower, it doesn't take as much heat to make the vapor pressure equal to the atmospheric pressure, so it boils at a lower temperature. So you can see there on Mount Everest, water will boil at 76 degrees, much lower than 100 degrees. So it depends on the atmosphere that you're boiling in. And also it's going to change a little bit depending on the weather. So if our atmospheric pressure increases, then our boiling point might go up just a little bit. Or if the barometer falls, if our atmospheric pressure falls, we might boil at a little lower temperature. But elevation is a big factor. On the flip side, what if you use a pressure cooker? Well, a pressure cooker actually takes the pressure, the atmospheric pressure above what you're cooking, and you are making it artificially higher. So in fact, a pressure cooker is much higher. I don't know what it is exactly, but it's way higher than 1 atmosphere. You're pumping it up so that you have a much higher atmospheric pressure. So what happens is that the water needs a lot more energy because the vapor pressure, even at 1 atmosphere, won't be high enough to boil. It has to boil at the higher pressure that's in the pressure cooker. So the temperature has to be much higher in order for boiling to take place. So in fact, in a standard pressure cooker, the water is actually boiling at 122 degrees rather than 100 degrees. And so what does that mean? Well, if you've got a higher temperature, then foods cook faster. So that's sort of the point of a pressure cooker, is to cook at a hotter temperature so that it cooks faster. All right, just a few more slides. We're just going to talk a little bit about why different liquids have different boiling points. And we touched on this just a little bit ago, but now we're going to kind of look at it. So, of course, not all liquids have the same boiling point. For example, oxygen, you can have oxygen as a liquid, but of course at normal temperatures, oxygen is a gas. At some point, you could cool it down cold enough to be a liquid. So its boiling point is very, very cold, negative hundreds of degrees Celsius. So why is oxygen not a liquid at room temperature? Now water we know boils at 100 degrees, but something like alcohol boils maybe at about 70 degrees. So why do they have different boiling points? Well, there's 3 different characteristics of molecules that will help determine where the boiling point will be compared to others. The first and very most important factor has to do with the types of interactions. So if the molecule is polar, there's polar interactions, which we know are stronger than nonpolar interactions. So if the molecule is nonpolar, it has weaker interactions. If a molecule is polar, it has stronger interactions. And then if there's hydrogen bonding going on, it has even stronger interactions. So that's the very most important effect or characteristic. But 2 others are also important: the size of the molecule and the shape of the molecule. So we're just going to look real briefly to those. So intermolecular forces, of course. So hydrogen bonding is the strongest, followed by dipole-dipole, followed by dispersion or the non-polar interactions. So if we compare, for example, water, H2O, which has a boiling point of 100 degrees, and methane, methane is a very non-polar molecule that only has weak dispersion forces. Because these are so very weak, you don't need very much energy to pull them apart, so it has a very much lower boiling point than water. In fact, boiling point for methane is a negative 164 degrees Celsius, so it is a gas at room temperature. Alcohol is also a polar molecule, but it's not as polar as water, so that's why alcohol boils maybe at about 78 degrees. It's lower than water because its interactions are not quite as strong as water. So of course this is the most important. However, the size of the molecule also matters. So if you compare methane, which we just looked at, it's a nonpolar molecule with very weak dispersion forces. But now C6H14 is also, that's hexane, which is one ingredient in gasoline. It's a larger hydrocarbon. It's still very nonpolar. It still only has dispersion forces, but because it's a much bigger molecule, there are more dispersion forces in general, and so the boiling point is a little bit higher. So the boiling point of hexane is a liquid at room temperature, and it's 69 degrees. So you can see that if everything else is the same, if they're both polar or they're both nonpolar, then the size of the molecule will be important. So CH4 is very small, it only weighs 16 grams per mole, whereas C6H4 is much larger, 6 carbons, 14 hydrogen. So it has it's a larger molecule, it has a higher boiling point. And then finally, the last thing, which is probably the least important, is the shape of the molecule. So here is the molecule pentane. Pentane is, again, similar, it's a fuel, sort of like butane. C5H12 actually can have many different shapes. So if you look over to the right, you'll see if it's in a big, long, skinny strand, it has a boiling point of 36 degrees, whereas if it's sort of in this little round, more symmetrical molecule, it has a boiling point of 9. So what's happening here is that when you've got long, skinny molecules, you have stronger dispersion forces because molecules can get a little bit closer to each other, and so the dispersion, there's more possibility of contact between molecules, so the dispersion forces are just a little bit higher, so it has a little bit higher boiling point. So just in summary, I guess your picture credits, you can look and see where I found my pictures. So there's 3 things that affect the boiling point of a liquid. The most important intermolecular interactions, hydrogen bonding stronger than dipole-dipole, which is stronger than dispersion, so that's the most important factor. Then the size of a molecule, if they're both nonpolar, the bigger molecule will have a higher boiling point. And then even if they're the same size, a longer, skinnier molecule will have a higher boiling point than a sort of squat molecule. So I hope that you have enjoyed this slideshow, and let me know if you have any questions.